So we're talking about applications of the dot product and the cross product. The first one that we want to talk about is projections. Now, to understand why we want to look at projections, let's go back and look at what we were doing when we first started talking about algebraic vectors. If we had some vector, we'll call it v here, and we took this vector v and we broke it down into its x component and its y component. So we said we could have a vector here along the x-axis, which we called x. We had a vector here that ran parallel to the y-axis that we called y. And what these things represented were, well, y here represented the component of v, our original vector, that was in a specific direction. It was in the same direction as the y-axis. So it's the component of v in the same direction as the y-axis. And similarly, if we had our x component was the component of v, or our original vector, that was in the same direction as our x-axis in this case. And we found these things using simple trigonometry. If we knew what this angle theta was in here, we knew that our x component had the magnitude, we just took the magnitude of v multiplied by cos theta, and that gave us the magnitude of that x component. Does this make sense? It's familiar here? Yeah, a little bit. Okay. Well, here's the question that projections sort of answer here. What if instead of trying to find the part of this vector v or this vector a that lies in the x direction and the y direction, what if we want the part of some vector that lies in the same direction as some other vector? Okay, so now we have two vectors, and we want to take vector a and say, I only want the part of vector a that is pointing in the same direction as vector b. Okay, and this is what components let us do. Projections let us do. It's like taking the component of a vector, but instead of taking the component that's along the x-axis and the y-axis, it's the component of the vector that is going in the same direction as some other vector. Okay, so we can do this. We can find the component in relative to any vector that we want. Okay, so this is where we're going with projections here. Why do we call these things projections? Well, let's take a look at the next slide here. And like most things in vectors here, I'm going to start by looking at these things geometrically, and then we're going to look at how you do this algebraically. So the way to visualize a projection is, imagine we've got our two vectors here, a and b. And because this is geometric, we know the angle in between them. It's theta. If we're talking about the projection of one vector onto another, okay, we've got to imagine that we've got a really bright source of light pointing from the ceiling down, so that these rays of light here that I've done in red are perpendicular to this vector b. Okay. What's going to happen here? Well, this vector a here is going to cast a shadow on vector b. Okay. That would be the edge of the shadow, like that. This thing right here, which is our shadow, okay, this is the projection of A onto B. Okay, so you're taking this A here and you're kind of flattening it down onto B here. So we'll call this thing C right here. And we'll make it a vector by saying that it always points in the same direction as vector b, because that's what we were going for, right? We were going for the part of A that points in the same direction as this other vector b. So C is the projection of A onto B. Now, how can we figure out, if C is a vector, how can we figure out the magnitude and direction of this vector? Looking at this information that we have right here. Yeah. Yeah. The magnitude of this projection is just given by, well, we know the angle between them, so we can do the magnitude of A times the cosine of the angle between them. Okay? That gives us the magnitude of the projection. What about the direction? Well, the direction we already know because that's what we were going for. We were going for the part of A that is going in the same direction as B. So the direction here has got to be in the same direction as B. So let's say the direction is, let's say, same direction as B. Now, if I just want to talk about the direction of B, I don't want to talk about the magnitude of B, just the direction. What did I use to talk only about the direction of a vector? Tim? Yeah, unit vector. So I can use that unit vector, B hat, to specify my direction. So we could say that here the projection of A onto B, vector C, is the magnitude of A cos theta B hat. And that gives us a vector. We've got magnitude and direction. Okay. So I'm going to put a little box around that. All right, so that's a geometric way of thinking about this projection thing. Now, I could have another situation. If I come over here to the right side here, again, I've got two vectors, A and B. I want to find the projection of A onto B. And let's just slide these things over here. Oh, nice little light rays. So imagine these rays of light coming down from the ceiling here, and we want to think about, if we're thinking about the projection of A onto B, we're thinking about what kind of shadow A, the vector A, is going to cast onto vector B. Well, the shadow of A is going to come down here like this. So our vector C is no longer in the same direction as B. It's in the opposite direction to B. Okay. So how is this going to change how our projection works here? Well, if we use this formula here, does this formula work anymore? What do we know about our angle theta here? It's not between A and C. Theta it's between A and B. But how big is this angle theta now? So what do we know about the cosine of theta if theta is greater than 90 degrees? Yeah, cos theta is going to be less than 0. It's going to be negative. So what this is going to do, this whole term here, A cos theta, is going to give us negative. So C is going to be, I mean, I shouldn't write the negative sign in there, but it's going to be the cosine theta, if we always use that angle theta between them, if it's going in the same direction as B, it gives us a positive answer. If C is going in the opposite direction, it's going to give us a negative answer. Okay? So it's automatically going to tell us that C is going in the opposite direction to vector B. Make sense? So this still works. So this tells us in the opposite direction to vector B. Okay. Okay, so let's see how we can go from this geometric interpretation to something that we can use on algebraic or Cartesian vectors here. So before we step on that, before we go into that step, let's just say that the notation that your textbook uses for projections is, if they want you to do a projection, they say projection of vector A is a subscript here, onto vector B. So you're projecting the vector from the subscript onto the bigger vector here. And geometrically, this is magnitude of A cos theta B hat. Okay? And I forgot the theta. Okay, what if we don't know what this angle is between our two vectors? Instead, we have two algebraic vectors, okay, given just by ordered pairs. What we know is that we can use the dot product which is equal to the magnitude of A times the magnitude of B times cos theta. So we have this relationship right here. We can use this relationship, A dot B equals magnitude A, magnitude B, cos theta, to replace some of the stuff that we have in here. So we've got A cos theta in here. So if we rearrange this for A cos theta is A dot B divided by the magnitude of B. Okay. So let's put this into our formula here for the projection. So our projection of A onto B is just going to be, instead of A cos theta, we'll put A dot B over the magnitude of B, and we've got B hat here still. Well, how did we calculate B hat? Well, B hat is a unit vector. We can always calculate a unit vector by taking the vector and dividing by the magnitude of the vector. So this expression becomes A dot B. If we substitute this in for B hat here, we get vector B over magnitude of B squared. So A dot B times B divided by the magnitude of B squared. Okay? And this is the formula that the textbook gives you for projection. Okay, this thing right here. And the one that I will sometimes use that I think is a little easier to remember is A dot B over B dot B times vector B. And those are the same as long as you remember that B dot B is the same as the magnitude of B squared. Okay. So those two things are equivalent there. Sometimes all you want is the magnitude of the projection, okay, rather than the direction, in which case we can just sort of take the magnitude of everything that we have in here, and we end up with the magnitude of A dot B divided by the magnitude of B. Because if we take the magnitude of vector B, it cancels out with the magnitude of B down in the denominator. Okay. So if you know these two formulas, okay, for the projection of A on B and the magnitude of the projection of A on B, that's enough to get you through most of the questions that you need here. Okay. So let's take a look at an example here. We got two vectors. Vector C, which is 2, -7, and vector D, which is 9, 12. We want to find the projection of vector C onto vector D. Right. So we're going to need that formula that we just developed. Projection of C onto D. Okay. And if we're doing C onto D, we're going to want C dot D up in the numerator. Okay. We want the magnitude of D squared down in the denominator, and we want to multiply this whole thing by vector D. So it's easiest probably just to work out each part of this little formula here independently. So let's start with C dot D. All right, we're just doing the dot product here, so we've got 2, -7 dotted with 9, 12. What are we going to get here? Well, let's see, we multiply the two x components, so 2 times 9 is 18. We're going to add to this what we get when we multiply the two y components together. So we've got -7 times 12 is -84. And we just add this stuff up. We get -66. Then we want, in the denominator, we want the magnitude of d squared. So the magnitude of d squared is just going to be, well, we just add our square our two components and add them up. So that's just going to be 9 squared plus 12 squared, which gives us 225. And then we can put all of this stuff together. The projection, again, we're doing the projection of C onto D, is going to be, we had -66 in our numerator, 225 in our denominator, and we want to multiply this by our vector D. Well, vector D was 9, 12. So we've got this scalar, -66 over 224, that we're multiplying by this vector, 9, 12. And so we just do this multiplication. At this point, we're just punching this into our calculator. -66 times 9 divided by 225 is going to give us something like -2.64. -66 times 12 divided by 225. Again, just punch it into our calculator. -3.52. Okay. And that vector there represents the projection of C onto D. Or this is the vector that is the component of C that points in the same direction as vector D. Okay? So let's save